With the mouse head tracking, this minion already feels alive. But what if we bring him into a 3D world? In this video, I'll show you how you can take this cursor tracking example and implement it in your Unity game so that the minion is looking wherever the camera is. Okay, so let's begin by taking a look at the animation in the Rive editor. So this is the original animation and it was designed to follow a mouse cursor. So you can see as the mouse changes its position on screen, the face is tracking that position. Additionally, if you move it far away enough, the animation goes to sleep, and if you enter again, the animation wakes up. And these are controlled through these inputs and listeners. We have one input called wake, which you can set to wake the animation. And then these three listeners are what are controlling the mouse position. So you can see we have a pointer enter, and once the pointer enters, we set the input wake to true, and pointer exit, we set wake to false. And then this final hit is a pointer move that is aligning a component called cursor. And this alignment is what is controlling where the animation is looking. So if we switch over to the design tab and we take a look at the cursor component over here, you can see as we move this right and left, the animation is looking in that direction, and up and down as well. And this is happening by also aligning the face control and this eye track. And if we disable this eye just so that we can make the pupil visible, you can see as we move the cursor, both the face control and eye track is following. And these are configured using a number of different constraints. And if you want a full tutorial on how to set up a head tracking rig, you can take a look at the tutorial linked above. It shows you the steps needed to configure a similar animation to the one in this video. If we jump back to this animation, all we need to do is align this cursor with some inputs that we're going to control from Unity. So let's just undo everything we did and get the cursor back to its previous position. And back in the animator mode, this is now where we will start messing around with the original animation. And because we're going to be controlling everything through code, we are going to be removing these three listeners. So I'm just going to right click and delete these. We're also going to change our artboard size to be a square. So selecting the artboard, I'm going to set the width to be 1000 and the height to also be 1000. And I'm just going to select the root container over here and just center it. And it's not exactly in the center. As you can see, this root is not exactly centered. So I'm just going to eyeball it, and that looks fine for now. If we go back to animate mode and now press play on the state machine, you can see that we need to call wake, but the moment we do, the animation jumps up from the bottom. And that is just because the wake animation has a keyed value for the root position, which we don't want for Unity. We want the position just to be consistent, and we want this to be as centered as possible. So if we play now and call wake, this looks okay. And I'm just going to set the default value to wake so that the animation always wakes up when we play it in Unity. Let's just bring back our animation in the center, and we're going to create two new inputs, and both of them are going to be a number. And I'm going to say that this is track_x and another one called track_y. And these are going to control the x-axis and y-axis look values. And let's start with x first, so the x-axis. And I'm going to create a new timeline or new animation. I'm going to call this base x, and another one called left x, and another called right x. And And for the base X, we're going to select our cursor and we're going to key the position, but just the X value. And then for left, we are going to play around with the position of the X by moving it left. But before we do that, just so that we can also see the pupil, I'm gonna make this invisible, the eye, so just that we can see. And back in animate, we're gonna select our cursor and I'm just gonna drag the X value to the left. And we're gonna do it until the pupil is all the way to the left. That looks okay. And you'll note that I'm only keying the X value, not the Y value, as we want these to be controlled separately. So next we're gonna go to right X and we're gonna do the same, just take it up and to the right. And that seems fine. So just to recap, we have our base X, which is the center, left, which is left, and right, which is right. So if we go to the state machine now, we're going to create a new blend. So I'm just first going to create a new layer, and we can say this is look or something similar to that. And within this look layer, we're going to create a new blend state, and we will add some timelines. The first timeline is going to be base X. Let's just move this out, base X, and this will be when the value is 0. And we'll do left X when the value is -100, and right X when the value is 100. So now we have this graph over here, and you can see if we play the animation, and currently nothing will happen because I did not configure the inputs here. So we need to select an input, say that track X will control this value. And if we play now, and if we start moving, it's still not going to do anything because you also need to connect to the blend state. So we don't want it from entry. Well, actually we do. From entry, we want it to immediately go into this blend state. So now if we play the animation, it should be exactly the same at the start. And then when we start tracking X and go to -100, you can see the animation is looking. And we now need to do the exact same, but we're going to do it in the Y-axis. So I'm just going to speed through doing that. Okay, so just to quickly recap, I created a new layer called Look Y, and I opted in to use 2 separate layers. So just to be consistent, we're going to call this Look X. And the Look X layer controls just the blend for the X axis, and Y will just control the blend for the Y axis. And it's exactly the same. We have our track Y input and base Y 0, bottom Y -100, top Y 100. If we play this animation now, you can see that we can control looking up, and we can also control looking left and right. So this is what we need to now get this animation working in Unity. So the final step for us would be to go download for runtime, and we can save this animation. Okay, so let's get started with the Unity part. And to begin, I've already created a sample scene. Very basic. You can just walk around and you can move your mouse to move the camera. You can do this in any way that you want. All you need access to for the Rive integration part is the camera. I will link a tutorial that shows you how to do this particular setup in this demo if you want to follow along exactly from start to finish. But again, you only need access to the camera to follow along with the Rive part. I also do recommend that you take a look at the documentation for Rive Unity. You can go over to the help.rive.app docs, and there you'll find a section for Unity and getting started instructions. And this may change in the future. So the scripts that are demonstrated in this video, there may be slight differences. So I do recommend that you always take a look at the documentation. especially if you use a later version of Unity than what is demonstrated in this video. Different version of Rive Unity, I should say. Additionally, you'll find there are Rive Unity examples. Here we will have updated examples that you can use, and this example demonstrated in this video will also be uploaded here, so you can find the full example code. And if you want to know what is the latest version of Rive Unity, head on over to rive.unity on GitHub, and here you'll find the tag section. Here you can get the latest tag. So at the time of recording, the latest version is 0.1.39. So we'll go over to getting started, and I'm just going to copy the HTTP URL for that particular tag. And if we head on over to Unity, we can go to Window, Package Manager, and then add from get URL. And I'm just going to paste in that URL. And the version is 0.1.39. And we can add the package. Once that is complete, you should see that the Rive package has been added. And if you ever want to update this, you can do that manually through code by going into packages, manifest.json, and here you can find Rive Unity and simply update the version number over here, and Unity should automatically update it next time you open. Okay, so Rive is added. Now we can proceed by adding our animation. And the first thing you'll do is just create a new folder for organization purposes, and I'm going to call this Rive. Then I'm going to select the animation that we exported, and in Unity, I'm just going to drag that into that folder. And now if we open the Rive folder, you can see that if you select the animation, it actually shows you a preview of it on the right side. And if you go back to the Rive documentation, here we have instructions on how to render a Rive to textures or to the camera. They effectively all render to a texture. And there's also different examples when you use the core Unity runtime, or if you use URP as a rendering pipeline. In this example, it is URP. So what we'll do now is we're going to create a script that will do the rendering of our Rive animation. So I'm just going to create a new C# script, and we can call this let's call this RiveTexture. And we can open that. So I already copied the code, and you can get the complete code from GitHub or from the help documentation. I'm just going to paste that in, and we can quickly discuss what is on screen. But before we delve into the code in depth, let's see what it looks like if we render our animation. Let's create a new quad. So go to 3D Objects, select Quad, and let's zoom into that. And then on this quad, I'm just going to drag in the RiveTexture. And you'll see that this particular script takes in an asset, which will be our Rive asset. So I'm just going to drag that in. And if we play our animation now, it should render this on screen. You'll also see that it has a size of 512. And if we take a look at the script, you'll see that that is the size of the render texture that this script is creating. So let's play that. And now if we jump on over here, you can see there is our animation. And this is currently rendering upside down. And just to fix this as a quick hack, we're going to go to the quad. And I'm just going to say that the scale is -1 in the y-axis. And that should work. Okay, so animation is playing and things are working. Okay, so our Rive animation is playing. Before we take a look at the code, let's just increase the size. So I'm just going to make this 3 or maybe 5. And let's move this up. And now in play mode, our animation is just a little bit bigger. Okay, so let's take a look at the code. You can see we have these 3 public arguments. Asset is our Rive asset. Fit is the way you want your Rive animation to be contained. And then the size is the size of our render texture that we will be creating. And you can see that these are what we are exposing, passing in the asset. Then the fit can be any of these options. If you want more information, you can find additional docs on the Rive website. Contain means that the animation will be contained in the available size. Then we have a few private variables that we will be initializing. And you can see that in the awake, this is where everything gets initialized. So we start off by creating a new render texture. And if you wanted to, you can also create a render texture by right-clicking, creating a new render texture. Where is that option? There we go, render texture. And you can pass in the reference like that. But for this sample, we are creating it for each instance of the quad, or maybe we should call this minion. So let's rename this. Because we want a new render texture for each of these to be created. We don't want there to be a shared one, and we also want it to be easier to recreate these. So now if we recreate a new one, each one will have a unique render texture automatically. And using this render texture, we are setting that as the texture for our material for the current component. So just getting the render and getting the material and setting that. Then we are creating a Rive render queue and passing in that render texture. And we're checking to see if the asset is not null. And if it's not null, then we are calling rive.file.load, which loads in our asset. And then we are getting the artboard at index 0. You can also pass in the name of the artboard. So if the artboard is called artboard 1, you can do that. But because this file only has one artboard, we can just get it by index 0. And this just calling state machine gets the default state machine on the current artboard. And you can also pass in the state machine name if you want to. If you don't pass in a name, it will just be the default. Next, we're checking to make sure that these aren't null. And if they're not, then we're calling the align method on our render queue. And this tells Rive how you want your animation to be aligned within the target render texture area. So you can specify the fit that we talked about in this section over here. And you can also pass in various alignments. Again, check the Rive documentation for more information. Next, you need to pass in the artboard that will be rendered. And finally, we are drawing our artboard. And we are then creating a command buffer. And this one also creates a command buffer. We actually don't need this call over here. I'm just going to comment that out. Creating our command buffer, and then we are setting our render target for this command buffer. And we're saying that it's the render texture. Then finally, we're clearing our render target before we do anything. And then using our Rive render queue, we are calling the add to command buffer, passing in the buffer. And then in the update method, we're calling render queue.submit, and this will draw the command buffer each frame. This is slightly different for URP compared to the core example, and you can find examples on GitHub. Additionally, in the future, a lot of this may be stripped out and hidden from you as an implementation detail. But for now, you can manage the command buffer yourself. And depending on the rendering pipeline that you use, it's slightly different. Finally, we need to advance the state machine. So we're checking to see if the state machine is not null. If it's not null, we call advance and we pass in the time.delta time. And advance is basically playing the animation. So if you wanted to play your animation at 2 times the speed, you can multiply this by 2 as an example. So if we go back into Unity, let's just make sure everything is still working. You can see that it is, and everything looks to be good. What we want to do now is update our state machine input so that we can control where the minion is looking at. And for that, we will create a new script, which we will call minion look script. And I'm just going to open that, and I'm just going to paste in the final code. And you'll see that this component requires the RiveTexture component as well. So that means when we add this minion look script, the RiveTexture will also be automatically added if it doesn't already exist. So we're going to select our minion, and we're just going to drag in our minion look script. And the damp values, I'm just going to set them to be the same default. I'll discuss them in a moment. So let's see what is happening in the script. We have a private state machine and two private SMI numbers. The SMI number is the number value of the state machine that we want to set. And those are these values, track Y and track X. And as we change these, it will change the area that the animation is looking in. So in the start method, what we'll first do is get the RiveTexture components, and here I'm calling it Rive Screen. A better name might be just RiveTexture. I did not want to capitalize that. And from this, we are getting the public state machine that is exposed. And once we have the state machine, we can call getNumber and pass in the name of the number that we want to get. So we're getting track X and track Y. And then we are also generating a new random time between 0 and 4 seconds. And we don't need to debug that. We're calling state machine advance, initially advancing the animation, so starting it up, and then calling advance again just by passing in this random time. And the reason for this is once we have a lot of minions on screen, we want them all to blink at separate times and move their mouse at separate times. So this just offsets the animations for each random instance. Then finally, in the update method, this is where we get to do the head tracking. And I'm going to talk about this in a moment. But now that we have the script, let's see if this is working in game. We'll play the animation. And you'll see that we are getting an exception. What we are missing here is we need to link the camera that we want to track. So selecting the minion, I am going to just drag in the player camera. And this can be any camera that you want to track. And now this should work. So let's play our animation, or play the game. And now you can see that the eye is following. And you may wonder what is the damp that we saw here. And you'll see once we take a look at the math behind this tracking, what that damp does. But now it is working. The only thing that's left for us to do is create more of these minions and explore how we're doing it. So let's exit play mode. Let's create a few duplicates of this minion. So I'm just going to drag out a few, put one there and one over here. And just make sure that it seems to be working. So you can see this one is looking us straight in the eye, and those are not looking us, or that the further ones are, I guess, moving their pupils. The description of that was lost on me just now, sorry. And additionally, if we were to make, let's say, this one a lot bigger, so let's make this 10, move it up, and just move it all the way to the back. You can see that once we get close enough, the eye should be going down more. And okay, so let's see what is actually happening in the code, and then we can start tweaking things. Okay, so now the code should make a little bit more sense. If we take a look at this update method, what we want to do is we want to calculate a dot product for our X and Y axis, and then set our look values to be equal to the dot product that's calculated. And this dot product will tell us whether the position of a vector is perpendicular to another vector or not. And the best way to illustrate that is if we take a look at the X product, you can see that we're taking the direction to the camera, and this direction to the camera will be the camera transform dot position subtracted by the transform dot position. So the current game object, which is the minion, we subtract that transform position from the camera's transform position. We normalize that value, and then we calculate the dot product based on transform dot right as our standard with this direction to camera. So if we log out this value, let's just say debug.log, and let's actually just for now, we will disable these two. So we just want one example running. You can see if we're to the left of the minion, the value is negative 0.7. If we go more left and to the right or forward, it gets closer to a value of -1. But if we go further to the right, it will get closer to a value of 1. And then if we are facing the game object, it should be close to 0. Eventually it should be 0 if you're exactly perpendicular. And this dot product allows us to determine what the angle is, or determine if two vectors are facing a similar direction. So it's telling us if the vector, which is just a right-facing vector, is equal to the direction of our minion versus the direction of our camera. And in a similar way, we can calculate that in the y value as well, just by passing in transform.up and passing in the same direction to camera vector that we calculated above. If we were to log the y value instead and play, you'll see that as we move around left and right, it's very consistently staying the same. But if we jump now, it becomes closer to 0. And if we go all the way to the top here, you can see that, or to the front, it becomes close to -1. And the further we go back, it goes closer to 0. If we were to go all the way up, then it would become closer to 1. So as an example, if we select the minion and just change its y to be below us, you can see eventually it gets closer to 1. Okay, but the question that remains is, what is the damp value that we have here? And that is just a bit of a programming hack, just because if we have this equal to 1, you'll see that it will have no effect, in that the calculation for times 1, it would do nothing. So let's see what it does look like when it's 1. You can see that the minion is looking all the way to the left, or his right, but it doesn't really make eye contact with us. If we have it as at 0, perfect, it's making eye contact. Here, it seems like he's looking too far to the right. So this damping value is just a way to quickly, through code, change the value instead of updating your state machine in the Rive editor. You can, of course, change it there, but this might just be quicker, just for experimentation purposes. So I found a value of 0.5, worked well in the x-axis. And now it seems like he's looking directly at us. And if we go here, it seems like he's looking directly down as well. And there we go. Something you may notice as well is, like, if we get close, it seems like he does get a little bit blurry. And that is what's nice if you manage the, let's see, the size yourself of the RiveTexture. So I'm just going to set this to be 0.5. And let's set the texture to 1024. And let's keep the Y damp at 1. Perfect. I think the wide amped one is perfect as well. And there we have it. That is how you can create a 3D tracking head in Rive and Unity. I hope you enjoyed this tutorial. If you want to find the complete source code, again, you can get that on GitHub. And if you have questions, feel free to ask that on our Discord channel or here on YouTube. And as always, we can't wait to see what you create.